Good morning. I'd like to describe today some work we've done using code reflection to translate Java to SPIR-V. In case you don't know what SPIR-V is, it's an abstract, I think of it as an abstract assembly language, SSA form, and it's a lot like LLVM in that regard. The SPIR stands for Standard Portable Intermediate Representation. And as Paul mentioned earlier, it's designed and managed by the Kronos Group, which is a consortium of companies that includes almost everybody. AMD and NVIDIA and Intel and Apple, a lot of other companies. There's a link with some more information. It's really good at expressing parallel compute and graphics, parallel graphics. All features, it's strict this way, all features are expressed as ops, and that makes it very extensible. You can think of it as a binary form. It's exchanged in a binary way. And right now, some frameworks, libraries that consume SPIR-V are OpenCL and Intel's Level 0 library, which is a low-level library that gives access to Intel's GPUs. We're using it with that. And some graphics libraries like Vulcan and OpenCL. So this first description of translations we're doing from Java happens in two phases. The first one is from code reflection, the low model, the low dialect, to code reflection, a new dialect we created called a SPIR-V dialect. And then a second phase where we go from that to a SPIR-V binary. I'll talk about a handful of tasks that are in that first phase, and one thing, the opt-op translation in the second phase. So there's a couple of good reasons, at least, for creating a new dialect in code reflection. And maybe the obvious one is when you have some Java code that you want to represent and process in a domain-specific form. One that I discovered in doing this work was having a dialect where you can do, you're doing structural changes and you're doing semantic changes, and being able to split that into smaller steps, having a dialect in the middle as a sort of halfway point, turned out to simplify the task overall. Creating a new dialect was surprisingly easy. You basically create a handful, whatever your set of op classes are, and have them extend the core op class. If your dialect needs any new types that aren't part of the Java type system, you can add them there. And then there's a couple of abstract methods in the core op base class that need to be implemented. As Paul said earlier, every op has a result type, and every op has to can participate in this transform API. We'll see a use of that API later. So I'm not going to go through the details of the code here, but I thought it was useful to put it in slides. This is our SPIR-V op base class, which extends op, and it carries that type element field. Some constructors and an accessor for the type. And then I'm showing one instance of a SPIR-V op class down below, inbound access chain. This is an op that computes pointers into SPIR-V composite types. We have a name that'll be used in text representations. And you'll see a pattern in all of these op classes where there's sort of a programmer's constructor where you can create an instance to add it into the output. And then there's a copy constructor. And this is important for this transformation API. And then we're implementing the transform API here. Basically, it's just, for this particular class, all of the state is handled in operands. So it's just a call to the copy constructor. So we have a couple of new types that are at least minimum types that have to be added to represent SPIR-V. And the one I'm showing here, or will show, is the SPIR-V pointer type. It uses these in loads and stores. It uses them in declarations, parameter declarations, and variable declarations. So we'll add a pointer type to the SPIR-V dialect, and it carries both a referent type. By the SPIR-V spec, it carries a referent type and what they call a storage class. So here's an empty base class. It's called SPIR-V type. It implements the type element interface. That makes it a proper type in code reflection. And the class here, the pointer type class, is really pretty straightforward. 2 fields to carry the referent type and the storage type, and then a constructor and accessors. We implement a method from the type element interface, externalize, and this gives us 2 things. It lets this type, if it's embedded in a model, be serializable. And it also gives us a nice representation in a 2-text transformation so that when we look at the output, it's easy to read. Implement equals and hash code in toString. So we have a dialect, we have our types added, and we want to do our main op-to-op translation. By the way, all of this is sort of a user's view of code reflection. I had nothing to do with the design of it. Just an interested party, making use of it. So when I first looked at this task, I saw it as 2 things. One is bookkeeping, and the second thing is just the mechanics of doing the translation. The bookkeeping boils down to mapping input blocks to output blocks. They're not actually output blocks yet. They're unbuilt, so they're in flight. So that's represented by a thing in the code reflection API called the block builder. And then we're mapping input values to output values. Typically, these are the results of input ops mapping to the results of output ops. But since code reflection uses this block parameter style of SSA representation, block parameters are a new kind of value. So if we're prepared to do that kind of bookkeeping, most of the translation from op to op turns out to be 3 steps. The first is you need to get your output operands. And these are typically acquired by just mapping the input operand values to the value map you're using to keep your bookkeeping. Now you have the operands, you can create your output op. It's sometimes more than one. If going to SPIR-V, some have a 2 or 3 op mapping on the output side. And then once you've added it, you have a new output. You have a new result, op result. And you want to complete your bookkeeping by writing a new mapping from the inputs op result to the outputs op result. That'll let you use that new result as an operand later. So here's some snippet of that main translation loop. I'm showing the declarations for these 2 bookkeeping maps, the mapping a block to a block builder and input value to output value. By the way, I started this before I really understood some of the sort of utility APIs that are also in code reflection. So you're seeing a manual, keeping of state, this bookkeeping state, and you're also seeing manual loops to sort of walk through the code model and do the translation. There's some shortcuts, and you can get rid of some of this boilerplate. We'll see that in an example later. But everything works out if you want to roll your own. So you can do anything you want custom, and it's no harder than these nested loops. So I'm showing just 3 ops on the Java side being translated to ops to this new SPIR-V dialect. Var load and a invoke and a equality op. And the 3 steps are just here. I wrote a utility method that just iterates through the input operands and looks up the output operands in this value map. And then we construct the output op with those operands. We add it to our output block, which I got from looking in the block map, and then critically, we make sure we keep our bookkeeping straight by creating a new map from the input op result to the output op result. Most of the translations I came across are kind of one-to-one. They have these 3 steps. Some ops have state other than what's carried in the operands. It might be, block references for branch ops, and those aren't values. Anything that's not a value, you're going to keep track of as fields in your op class. And when you do the translation, you'll have to do whatever it takes to map the input version of, say, a block reference to the output, because since they're immutable, those can't be copied across. They're unique. You need to do a mapping. In the last case here, SPIR-V has type-specific ops for equality, where Java uses a generic one. So there's some specialization done in that case. So if that's all there was, we'd be done getting to the SPIR-V dialect, representation. And most of the work was straightforward like that. There were a couple of structural things that didn't match between code reflection and SPIR-V. And I'll just walk through a couple of those that we're done now. The first one is a pre-step to the main translation, and the second is a post-step. In code reflection, variable ops are like you might think of an assignment, a declaration and assignment in Java. They appear relative to their position in Java source, and they can have an initialization operand. But in SPIR-V, they're pure declarations. And there's a rule: they have to be the first ops in a function's entry block. So the position of them in the Java model is not quite right. Even though all the information we have, we're going to declare a type like that, we're going to initialize with that value, but it needs to be split up for SPIR-V. So in the translation, we're going to lift all the variable ops for SPIR-V to the top and put them in the entry block, just as declarations. And then in the original position of the Java var op, we're going to take the right-hand side of that var, which is the initialization value, and we'll create a store into the variable we declare at the top. So it's very straightforward, but it's kind of this awkward reorganization of ops. And it was something that wasn't just a linear mapping from op to op. So this is the code that does that. The first set of loops there just iterates through all the blocks and all the ops in them. And when it comes across a core op, var op, it'll create a SPIR-V variable op with a pointer type as its part of its declaration. And then it will add it to the entry block of the output function we're creating. Since we created a new op, we need to add to the bookkeeping the mapping of the input op result to the output op result. So now we enter the main translation loop we saw earlier, but with this pre-step done, we're ready to handle the differences between variable ops. So I'm showing just one op in this version of the main translation loop, and that's the core op var op. And this is just going to create a store that will extract the operand from the core op var op's first operand. It has one operand. And then it uses that as the initialization value in creating a store. There's no mapping to be done here. Store ops, I think mechanically they have an op result, but it doesn't mean anything. And so there's no need to handle the creation of a new mapping. So here's more of a complete example. The Java method in the upper left-hand corner it's a very trivial kernel. It's written in the style of the heterogeneous acceleration toolkit that you'll hear about. And the model code down below it is the low dialect that was just returned by asking code reflection for the code model. So we've translated that to the right-hand side. It looks very similar. You see the variables are moved to the top. We're using the pointer types up there. And that's the first rendition of a SPIR-V dialect, the translation from the low dialect of code reflection to a SPIR-V dialect of code reflection. So another difference between the SPIR-V dialect and the code reflection dialect is that, as Paul explained, the code reflection uses the block parameter of SSA representation, and SPIR-V uses FIOPS. It doesn't support the block parameter style, so at some point we need to convert from one to the other. In the implementation of this, it's done in a couple of phases. The first one just analyzes the existing incoming SPIR-V model and builds some data describing where the FIOPS have to go and what their operands will be. And then we walk through the code in a transformation to simply add the FIOPS. In case you're not that familiar with maybe the block parameter style, I wasn't. Here's just a little bit of code that describes what we're trying to go from and what we're trying to go to. In this sample, it's that scale kernel. I pulled out 3 blocks, block 1 and block 2, both branched to block 3. And because there was a ternary expression in the kernel, we're going to have some values that cross that code, cross that control flow. And so we have a block parameter in the destination. In the target, block 3 has a block parameter, %21. What we want to do to get the FIOPS is simply add a FIOP to block 3 with information about the predecessors and the values associated with those branch points. The second thing we want to do in addition to adding the phi is we want to disable the block parameter use and replace any occurrences of a block parameter use with use of the FIOP result. So you see that here. We have a store at the bottom that was using the block parameter to initialize a variable up top, new value, and we wanted to be using the result of the FIOP instead. So the first part of that, the first step was to build this map. And I'm not going to walk through the code in detail, but describing it at a high level, we're walking through all the blocks and all the ops, and we're just going to examine the branch ops. And what we want to do is we want to create the data we need for the operands of the phi we're going to insert. So it's just collecting pairs of information about the predecessor, a reference to the predecessor block, and the value associated with that. A block can have multiple parameters, and so we need to be able to add multiple phis per target block. And so there's the phi map is a nested structure mapping a target block to a list of pairs of block reference and value. You see the use of the code reflection API, and it might not be obvious, but it made it very simple to actually do this kind of analysis and building of this data structure. So armed with that data structure, we can, you'll see, we call the method shown on the previous slide as the first line there. And then we're gonna call a transform method on the input SPIR-V function. And our goal here is to do those two things, is to add the FIOPS and sort of switch uses, turn off the use of block reflection, turn on use of I'm saying phi and I'm saying phi because I asked somebody what the most common one, and a senior person at my company said phi, and I heard Paul saying phi today, so I'm really mixed up. I've read a lot about what the people want to call that, and I realized there's no answer. Anyhow, so we're going to call the transform API on the func op, and we're going to see that this is doing a similar walking through all the blocks and all the ops, but a lot of the boilerplate is now removed because we don't have to maintain our own bookkeeping data structures. Those are maintained for us. And we don't have to manually write our loops to iterate. That iteration is being done in a more straightforward way. So the funcob.transform, what it takes is a lambda that will give you two things. It gives you a block builder, a block in flight, and that's the output block that's in flight. And it gives you an op, which is the input op you're going to transform from. And so when we begin iterating using this transform API, we're going to look at the phi map we created before. And if there's an entry for the block associated with this op, we know that that's a target block that has a block parameter, and we need to add one or more phi ops to that block. So the rest of this code is just mapping information about the input predecessor information, the source blocks, and into the output predecessor information, and then creating the phi op using that operand information and adding it to the builder, the block builder's output. It's easy to miss this next step. I had a bug here at first because we created a new op. We're transforming from one version of the function to the next, but we inserted a new op, and we want the value associated with that to be, first of all, visible. And in our case, this is the way we do that substitution from use of a block parameter to use of a phi op result. And so one line of code, we just ask the builder to get its context. That's a thing called a copy context, and that's what keeps these bookkeeping structures for you. And since it's got a value map in there, it offers a map value function, and the input mapping is the parameter we want to turn off and replace with the phi op result. That's the right-hand side, the output result. And we're done with this block, so we remove it. We do it we do all the phi op processing for a block all in one place here. And then another line that isn't obvious maybe, but you're doing a transformation. You want to keep, in this case, all the original input ops. We're just adding ops here. So I have to make sure that I have the builder simply add the op that was passed in. It's easier to do this than it is to talk about it. And there isn't a lot of code here, and a lot of boilerplate is removed by the use of this transform API. I think I'd like to use it more instead of the nested loops and keeping your data structures yourself. But it's a testament to the flexibility of the API that you can do it either way really well. If you have something that doesn't fit these built-in transform APIs, you certainly can roll your own. I liked using this. Okay, this is just showing you the output, the SPIR-V dialect coming in using block parameters, and the SPIR-V dialect going out using the phi ops. The second phase in this translation to binary is going from that SPIR-V dialect model we just built and to a binary. And for this phase, I use a library called the Beehive SPIR-V toolkit. This is written by the same people who do the Tornado VM, and it's a really nice library. It's well thought out, and it's easy to use. It's pure Java. In this translation, there's familiar bookkeeping. It's just that we're going from the code reflection world to outside the code reflection world into somebody else's model. But we still have block maps, and we still have essentially value maps. We're mapping to SPIR-V IDs in the binary side. And in principle, because we've done all the SPIR-V semantics and mechanics and put them in the SPIR-V dialect we created, this should just be a linear mapping. And I think it will be out of just not getting to it yet. Some of the op creation that's required for the binary side is not done until this phase, but it could easily be moved up into the creation of the SPIR-V. Like, type in SPIR-V, all types have to be specifically declared, even integer types. If you want an int32, you have to declare it as an op in the SPIR-V binary. That is still only done in the translation to the binary right now, but there's nothing missing that I can see in the code reflection API or framework that wouldn't allow you to move all of those low-level ops up into the SPIR-V dialect, where we have an API that's really good for analysis and transformation. Even though, some of this is incomplete at this point, the two things that were moved up into this, they were originally done in the translation from Java code model to the binary, but moving this variable relocation around and the FIOP translation into the creation of the SPIR-V dialect really simplified the binary translation. Everything was sort of layered all in one phase before, and splitting those into two, that was reason enough in my mind for having a dialect, a SPIR-V dialect. So I won't walk through this at all. This is just the same kind of nested translation from a SPIR-V op to a SPIR-V binary op using the Beehive toolkit library. And this is the text output from that. On the right-hand side, we have the disassembly of the SPIR-V binary. Most of this is really about translation. I wanted to talk about code reflections use in this translation, but I thought one slide to show how we can use Java to continue the mission here and actually do the running. So the way the testing of all this translation has been done using an early version of a SPIR-V hat backend. And so we're running these little GPU kernels, or not so little, by first translating to our SPIR-V binary, which is what our Intel GPUs accept. And then we're running them with a stack that looks like this. That kernel launcher is really the hat backend, the SPIR-V backend. And we've created our SPIR-V binary. Now we just create args for the kernel. And we do all of this using a Java binding to the Intel level 0 library. And this binding was created by just pointing the level 0 header file, giving it to JExtract. And it built a very complete and usable binding to the level 0 library. So one of the things we can do there is allocate memory on the host or on the device or shared memory. So we do that. And then we wrap a memory segment around there using FFM. And then we initialize that memory segment with the kernel's data. We make another level 0 call through the binding, sending both the binary and the args to a command queue in level 0 for execution. So it's all Java code that was written here. I thought that was nice. Okay, that's the GPU translation that we've been working on. I'd like to talk about some work also using code reflection for translation done by a colleague of mine, and it involves Triton. I won't go into deep detail. Triton's a Python-like DSL that allows people without low-level GPU programming experience to write really efficient code, like 10x faster than good scalar code. Paul Sandos wrote as he referenced this Java Triton front end, a model creator, and that's at that link in the repo, the Babylon repo. There's also a great Triton blog article that he wrote that's been helpful. So what the front end produces, the Triton front end produces is the Triton dialect of code reflection, and that's what we'll start with. The idea was to take that starting point and hook it up to a Triton backend. And so we hook it up to Intel's Triton backend shown at that link. That's the GitHub project. I copied this directly from the Babylon repo. This is just a really simple kernel. It's one of the examples in that example directory. Add kernel takes two vectors and just adds them together. I'm using that because, again, it all fits on a slide. So this is just an overview of how the POC for hooking the two is structured. The white box on the top, we're starting with. The white box on the bottom, we're starting with the Triton front end and the Triton back end. The code in green is what my colleague wrote, and it takes the Triton code model and it converts it to MLIR Triton text. So we're doing it as text because it's hard to get at a builder API for MLIR that's callable directly from Java. But because we knew the backend could accept MLIR text, and because we had a very fortuitous starting point, which is the code reflection operator class, the class that takes code model ops and writes them out as text. The output of that wasn't that different from what Triton looks like in its text form. So my colleague started with that. And the backend then accepts that text and creates an in-model, in-memory version of that. It gets lowered to a GPU dialect that Triton has. It then gets lowered to LLVM. And then the Intel backend produces a SPIR-V binary from that. Here's the code reflection produced by just asking for the code model of that small Triton kernel. And that gets translated by this POC to this code. And it's not that much different. It's just that this is now legal Triton code, and we could submit it to presumably, anything that consumes Triton MLIR. And we only use the Intel backend in this case for translation. We're doing all the running in a stack that's with just Java code, with a stack that's the same, essentially, that we're using to run other GPU code. There's a little bit different launcher, and creating the args is a little different. There are some temporaries that Triton creates in its translation. But then we execute it using the Java binding to level 0. So let's see. It's really just a statement here that code reflection works really well for this in the hands of somebody who is not, I haven't made my career as a compiler engineer, and I didn't really understand the MLIR style, data structure nesting. There are a lot of things I didn't know at the beginning, but you just sit down with this API and you look at examples and you look at the code reflection source code and lots of, it's easy to learn. And for anyone, I think, but especially for me, it made this work approachable, and it took heroics out of it. The things that presented challenges originally were just the bookkeeping, keeping the input and output values mapped so that they were available later. And just remembering the differences between sort of input things that are built or bound and output things that are in flight, because what you can say and do with those is different. Things that felt really simple from the beginning was just getting at the code, inspecting it, looking at it, and doing the iteration you needed to do analysis and transformation. It was easy to do with the manual loops because I knew how to write those, and they all just worked. And it was even easier to use something like the transform API because a lot of that boilerplate left. So it's a very happy experience using code reflection for these tasks. That's all I had.
So when we started this project, we imagined, the kind of thing that you're doing where you're translating Java code to a foreign execution model. And one of the things that we knew we were going to learn something about, but didn't quite know what we were going to learn, is how to describe limitations on the subset of Java programs you can write that would translate cleanly to SQL or SPIR-V or whatever your backend is. So you showed a lot about the tree transformation and the control flow analysis and all of that. Did you start with a clear specification of what Java code you can run, what Java code you couldn't run, or was it sort of a more ad hoc, just give up if you see anything that you don't, that you don't know how to transform?
Yeah, that's a really good question and something that's been talked about a lot, the subsetting problem. I think my cop-out answer would be it depends on the model you're defining. So Triton defines a model, and I think, that, for example, in that example, that would tell, that would describe what parts or semantics that are now represented in Java are translatable to the thing. For GPU, I know that, I've talked with the Tornado VM folks, and we've had discussions about the subsetting issue, because they originally supported, native arrays, and I wrote code to support native arrays. I thought that was interesting. It turns out there's lots of, as you can imagine, difficulties with memory management and so forth, or overhead of copying. And so it's an open question. I think that if you look at what Tornado VM is doing now, they've dropped use of native Java types. It's all just, things described by a specification and contained by a memory segment and a layout maybe. And I know that that's where Hat's going with a lot of the data type support. So I don't have to have an answer. I'm really convinced that any model that you present that's representable as Java, if it's reflectable, can target any hardware that has a rigorous description of what's supported there and what's supported there. SPIR-V supports this notion of capabilities. You can have addresses, you can have 64-bit addresses, you can have vectors and so forth. So, there is a hardware to software mapping, and then there's a model to translation mapping. But in this case, we're still at the building the model phase. So the SPIR-V translator is not trying to answer it. It's just trying to accommodate whatever the model describes.
You've been describing a tool that somebody is going to use, presumably to get performance improvements. Can you talk a little bit about the layer above? What is the user experience like for somebody who has your translation tool and is using the API? What sort of code are they going to write, and what are they going to gain out of that?
So if it's a GPU model like Hat, let's say, you can write anything that you might have written in CUDA or that type of thing. And so at the high level, what I've been experimenting with is, really well-known GPU kernels like matrix multiplication to see, different ways you might translate it to generate vector code. For example, SPIR-V, allows you to express vector code or scalar code. The limits there, again, are kind of described, I think, by the programming model, in this case, a GPU programming model. There have been, surprising difficulties in that higher level, implementation. So, if you don't have a well-defined kind of modular programming model where you're expecting different backends or different implementations, it can be, kind of ad hoc and real messy. But there's a lot of work going into that in Hat to make sure that the rigor and the flexibility of those Hat's and backends at least demonstrate the ability to have multiple backends and do the whole stack from Java source all the way through code reflection to whatever NVIDIA or Intel or AMD or whatever the target is. So my experience with the high-level thing is that you need a good model. We have a Triton model. We have a Hat model. And I tell you one thing is that code reflection and having this experience makes me really ambitious with programming models for targeting specific hardware or targeting semantics that aren't easy to guarantee in Java. Let's say you want deterministic semantics. That's not that easy to express in Java. But with some, translation, you could do that, a subsetting defined by a model, and translation. Now you have a plugin for Java that, whether or not it's going to Java or going to, other hardware, it's enabling this ambition to have programming models, other than the one we all love, as a place to go, a place to explore. Looks like that's it. Thanks a lot. Thank you.